All right, so welcome to 11.6 on optimization. So here we're going to look at areas and perimeters, maximizing revenue and profit, as well as inventory control. So what we can do is use that calculus to solve optimization problems. So problems that are involved finding the absolute maximum or the absolute minimum of a function. Now note that the statement of the problem does not usually include the function to be optimized in this section. So often it's going to be your responsibility to find the function and then to find the relevant absolute extremum. Okay, so that's going to be the key. They don't always give us what we need to do here. And that happens here in the first case where we're maximizing areas. So homeowner has $320 to spend on building a fence around a rectangular garden. Three sides of the fence will be constructed with wire fencing at a cost of $2 per linear foot. And then the fourth side will be constructed with wood fencing that costs $8 per linear foot. And we're supposed to find the dimensions of the area of the largest garden that can be enclosed with $320 worth of fencing. All right, so let's kind of maybe think about drawing a picture here. A rectangular garden will look something like this. And we know we've got $2 per linear foot on some of the sides. So we'll put it on the longest sides for sure and one of the shorter sides. And then we'll put the $8 for the other one. If we want to maximize our fencing based on prices, we're going to probably want the least amount of the $8. So that will give us kind of that edge. All right. So then what do we have? Well, this is area. So area is equal to length times width or x times y, depending on what variables we want to use. Now, if we say we have maybe these are x's and these are y's, then what we could do is we could say, okay, well, uh, we could come up with a perimeter because that's how we're going to do a fence. The perimeter is going to be what? Well, that's going to be equal to, well, we're going to have 2y's plus 2y's plus 2x plus 8x. And we know that if we take x times y, $2 by the x, which is, the linear feet, so it's going to be end up giving us a value of dollars, then that has to equal our 320. So the perimeter is really it's perimeter times, I guess, a dollar sign. So it's going to be a perimeter times a dollar. And so we're having a dollar times a piece of the perimeter plus a dollar times a piece of perimeter. And then that total gives you the total dollars. Okay. So now we have that. Now let's simplify this. So 320 equals what? Well, there's going to be 4x plus, or wait, 4y rather, plus 10x. Okay. And so when we get that, that's going to be our cost because we know that's that. So if we want to label it, we can say, okay, that's our cost. We don't have to at this point, but eventually we might want to. So now let's solve this equation for maybe x. And it doesn't matter, you could solve for x or y, but I'm just going to solve for x. And so if I take 320, take the 4y over, that'd be minus 4y, and that equals 10x divided by 10. And so x is equal to 32 plus 0.4y. Okay. Again, just dividing by 10, that's all I did here. Now, area is going to be what? Well, area now, coming back up to here, x times y. Well, x, we just said was this. And if we multiply that by y, we're going to get what? We're going to get 32 plus 0.4y times y. And if we simplify that, that gives us a of y is equal to 32y plus 0.4y squared. Okay. Now, what do we know about y? The length and the width, actually, x and the y, all of them have to be greater than equal to 0. So the length and the width have to be greater than or equal to 0. This great equal to probably doesn't make sense because you're not going to have a length of that side, but the greater than for sure is going to be a key piece here. And so if we do that, now let's go back down to this one here. Well, this then 32 plus 0.4y, that has to be what? Well, that has to be greater than or equal to 0. So we're kind of going about this as we think about pieces here. So now if we do that, now we can solve this for y. And so if we subtract 32 over, then we'll have a 0.4y is greater than or equal to 32, divide by, oops, oh, that was weird. What happened here? Okay, divide, let's see what we have here. What do we have? What did, okay, there we go. Divide by, where'd my cursor go now? There we go, 0.4 and 0.4. And so then here, y has to be less than or equal to what? Because let's see, greater than, oops, that's a negative here. That's why this isn't looking right. It's like, wait a minute, this should be this way. All right, so it's a minus. Got to keep the minus here. That's a minus up there. We better keep the minus there. We're going to be really in trouble here in a little bit. All right, so that's a minus, and then that's going to be greater than equal to, but then when you divide by it, it's going to be less than. And so we took and subtracted the 32, so it's a minus 32, and so that's going to be 32 divided by 4 is 8. Move the decimal 1 over, so that's 80. And then that's a minus, and that's a minus. All right, so I think we're caught up with the error we made over here with this negative here. All right. So now that means y is less than or equal to 80. Well, we said that the x had to be greater than or equal to 0. And so then this gives us then that 0 is going to be less than or equal to y is going to be less than or equal to 80. So it has to be greater than 0, but less than 80. And so now what we're going to do is we're going to kind of find out what x's and y's are. Okay. So we want to basically, that's our area equation. So we want to maximize that, right? Because that's what we want to do, maximize area. So if we do that, that means we're going to first take our first derivative. So that's going to be 32 minus, and that's going to give us 0.8, and then that's going to just be a y. Now, if we solve that and set that equal to 0, 32 minus 0.8y equals 0, subtract 32 0.8y equals 32 because we're going to divide by negative, and then we divide by 0.8. And so y then is equal to, it looks like 40. Okay. And so that would be our value there. Now, the next thing we're going to do then is plug that back in over here. And so x is going to be equal what? Well, it's going to be 32 minus 0.4 times 40. So that's going to be what, 16? And so that's going to be 32 minus 16 is 16. So that's going to be what x is equal to. All right, so x, that's going to be this. So one side of our fence, so now that we've got all that, and these are in feet, so that would be 40 feet, 16 feet. So we've got this new picture drawn. Now we've got 40 feet this way, 16 feet this way. And so now we can say one 16-foot side is going to be made out of what? It's going to be made out of the $8 per linear foot. So is made of $8 per foot wood. And then the other sides are the $2 per foot wood. Oh, that's wire. Sorry, not wood. Okay. So now we know all those sides. And so now what would our area be? Because it says find the dimensions and the area of the largest garden. Well, our dimensions are 40 foot by 16 feet. And if we take that and multiply it out, area is going to be 16 by 40, which is going to give us 640 square feet inside of our rectangle. So that's going to be the maximum area. And again, one of the 16-foot sides is going to be made of the $8 per square foot wood, and the other three sides are going to be the $2 per square foot wire. Okay. All right, so let's stop there and we'll come back for some more.